or yanking her computer. It's my great privilege to introduce our colloquium speaker today, Dr. Leslie Rogers. And just go through her CV just really briefly here. She got her bachelor's degree in physics and mathematics from the University of Ottawa in Canada. From there, she went on to get her PhD in physics from MIT. After that, she won a Hubble Fellowship, and I was fortunate enough to entice her to come to Caltech and be a part of the Caltech Exolab at the time. So it was wonderful having her as our resident theorist. And while she was there, she worked with one of our current first years, Alan Price, and they wrote 2 papers together. Was it? Yeah, 2 papers together so far, with a third in progress. So she'll be continuing to be a Hubble Fellow through the, well, actually, is that?
No, I've officially transitioned.
Now you've already transitioned, yeah, because in August she took up a Sagan Fellowship at UC Berkeley, and she's only going to do that for a year because she's going to be an assistant professor at Chicago starting next fall. So she'll be joining the growing exoplanet group there that includes Jacob Bean, who we know well from here, and also Dan Fabrici. So among the many awards that are listed on her CV, which include at least 1 gold medal and 1 silver medal, because I suppose they give medals in Canada.
Yeah.
She's also a Lindo Nobel laureate junior scholar, where she got to meet Nobel laureates in the 2012 meeting. And they cycle through topics every 3 years. So this year, physics is up again, and I believe they're taking applications for the next set of junior scholars. So for anybody interested in the room, I'm applying for that. And so with that, I think I'll hand it over to Leslie, and she's going to be talking to us about the diversity and demographics of distant rocky worlds. So take it away.
Thank you. So it's a pleasure to be here. So in my research, I work at the intersection between astronomy, physics, planetary science, and statistics to try to unravel insights into the diversity and formation mechanisms of exoplanets. And much of my work involves modeling the interior structure and evolution of these planets. So that will definitely bias the topics that I present and kind of the perspective that I offer you today. So we now know that when we look up at the sky, almost every star that we see is orbited by planets. And there are several thousands of these exoplanets, planets outside the solar system, discovered to date by several different techniques, including radio velocities, transits, direct imaging, and microlensing. Now, there's a wide range of diversity and exotic surprises among this sample of planets that has been discovered to date. From the initial surprise of discovering hot Jupiter planets on 3-day orbits around their host stars, to tiny, evaporating rocky planets on ultra-short period orbits, all the way out to free-floating planets that aren't associated with any star at all. So among this wide range of diversity and exotic surprises, today in my talk, I'm just going to focus on the rocky worlds, the rocky planets. And I certainly don't mean to imply that they're the only planets of interest. I love hot Jupiters and Neptunes as well. Nor do I mean to imply that these might be the only types of worlds on which life might eventually evolve. But these rocky planets are of interest, perhaps because they provide environments that may be a bit more familiar, that we might visit with our imaginations, if not with our spacecrafts. So in my presentation today, I'm going to focus on 3 key questions related to rocky exoplanets and describe some of the current empirical constraints that we have on each of these. So first, how common are these small exoplanets? Which of the planets discovered to date are rocky? And how Earth-like are these rocky bodies? Okay, so now let me get started with this first item. So in terms of constraining occurrence rates of planets, well, the Kepler mission that we all know and love is the current record holder planet survey that has discovered and characterized more exoplanets and planet candidates than any other. So here I'm showing an example radius distribution for planets orbiting G and K stars derived by Eric Pettigrew and collaborators from Kepler statistics. So this is planet size on the horizontal axis, and then the fraction of stars with planets on orbital periods between 5 and 100 days. And here you can see clearly that at least on this range of orbital periods, smaller planets are far more common than larger planets. Based on these statistics, planets smaller than 4 Earth radii, planets smaller than Neptune, outnumber planets larger than Neptune on this range of orbital periods by more than an order of magnitude. So this is the result. These are some of the results from the Kepler Transit Survey, but they show broad qualitative agreement with other survey techniques as well. So both microlensing and radio velocities have also found that smaller planets, or at least lower mass planets, tend to be more common than their Jovian counterparts on the range of orbits close in and out towards the habitable zone in which each technique is sensitive. Okay, so already we can say that roughly 50% of G and K stars have planets smaller than Neptune on this range of close-in orbital periods between 5 and 100 days. Currently, extending the occurrence rate, at least for G-dwarf stars, out to the habitable zone, where liquid water might persist on the surface of these planets, is an extrapolation. So, but now, among these sub-Neptune-size planets that we've been cataloging and characterizing, which of these planets are rocky? So within the solar system, there's this order of magnitude gap in mass between the terrestrial planets, the largest of which is the Earth, down at 1 Earth mass, 1 Earth radius, and the ice giants, Uranus and Neptune. And now among exoplanetary systems, we've been filling in this gap. So are these super Earth and sub-Neptune-sized planets scaled up rocky bodies, scaled down mini Neptunes, or something completely different? This is an important question for interpreting the broader radius distribution discovered or characterized by Kepler. So when Kepler sees, say, a 1.6 Earth radius planet in the habitable zone of its star, is that planet more likely to be rocky or volatile rich? What about a 2 Earth radius planet or a 1.5 Earth radius planet? How does the fraction of planets that are rocky vary as a function of planet size? To address this question, we can turn our sights to the valuable subset of planets that are detected both in transit and with radial velocities or transit timing variations. Because from the planet radius measured from the transit depth, and with a planet mass measured from the planet's gravitational influence on its host star or other planets in the system, mass and radius together combine to give the planet mean density and some handle on the planet's bulk composition. So here I'm showing a planet mass radius diagram. And both axes are in Earth-based units. Each of these solid curves, or each of these colored curves, are theoretical mass-radius relationships for constant compositions. So the solid blue, red, and magenta curves are for hypothetical pure water ice, silicon, and iron planets, respectively. And this is literally what this diagram looked like 8 years ago when I first started studying planets. Back then, we knew of the solar system planets, of course, but a transiting Neptune-sized planet was a purely theoretical concept. Of course, over the past decade, planet hunters have been populating this diagram, and the Kepler mission has made a huge contribution to that. In addition to planet mass and radius, from the planet's orbital period and from characterizing the planet's host star, we also have a measure of the amount of irradiation that each of these planets is receiving, which I'm showing here according to the color bar, according to the color of each point. So here the color bar scale represents the amount of irradiation flux received by the planet scaled to that of the Earth, and it's on a logarithmic scale. So you'll note, pretty much from this scale, pretty much all the planets on this plot to date are more strongly irradiated by their stars than the Earth is by our sun. And that's just due to the selection effects and biases inherent in the transit and radial velocity techniques. But coming back to this question of which planets among these might be rocky. Well, for that, let me draw your attention to this mass-radius relationship for a pure silicate composition. In some ways, this is a robust upper limit on the radius of a rocky planet of a given mass. Planets that are less dense than this require some volatiles, either in the form of astrophysical ices or hydrogen-helium, to contribute to their transit depth, to give their low apparent mean density. Whereas planets that are more dense than this might be potentially comprised of iron and silicates alone. And so you might already be able to see by eye this trend in the data. So there's a paucity of planets in this lower right-hand corner. And this represents essentially a lack of very massive, high-density, potentially rocky planets that have been discovered to date. And so in order to address this question of how does the fraction of planets that are sufficiently dense to be rocky vary with planet size, I essentially sought, with a use of population statistics, to set this trend we can already see by eye in the mass radius diagram on a robust statistical footing. So using the sample of Kepler planets with radial velocity masses measured by the Keck high-res spectrograph, I applied a hierarchical Bayesian modeling approach to see what that sample of noisy mass radius measurements tells us about this transition between rocky and non-rocky planets. And so let me show you some of these results. So here I'm showing results for how this fraction of planets that are rocky at a given size on this vertical axis, and then this is planet size in Earth radii on the horizontal axis. And the color scaling of this plot just represents the posterior probability distribution for F rocky at a given value of planet radius, conditioned on the sample of Kepler planets with Keck radial velocity masses. Now, to read this diagram, let me walk you through it. So if you're interested in planets of a given size, let's say 2 Earth radii, you'll look at a vertical slice through this diagram. The planets, or values of F rocky that are shaded red along this slice, are more strongly favored by this sample of mass radius measurements, whereas values that are shaded blue are largely ruled out. And you could repeat that at any particular radius. Integrated over a vertical slice, this posterior probability sums to 1. Though there can be a discontinuity here, both at 0 and 1. for anyone who's now trying to do the integrations in their head. So this blue region here in the upper right-hand corner is essentially putting on the robust statistical footing that feature we could see by eye in the mass radius diagram. So this is saying that we've essentially, with the current data in hand, ruled out the possibility that majority of planets at 2 Earth radii or 2.5 Earth radii are rocky. In fact, by the time we get up to 1.6 Earth radii, we can say with a high degree of confidence that fewer than 50% of planets at that size are sufficiently dense to be rocky, at least on the range of orbital periods, typically interior to 50 days, that this radial velocity sample, this Kepler plus Keck radial velocity sample, is currently probing. And so this is the main point to take away from this portion of my talk, is that at least among this close-in sample, most 1.6 Earth radius planets are not rocky. They require a volatile envelope that contributes to their transit depth. So this gives us some insights into how to interpret the remaining majority of Kepler planets for which we do not have direct measurements of their masses. And since one of the main motivating goals of the Kepler mission was to characterize the occurrence of Earth-like planets on Earth-like orbits around Sun-like stars, this also helps to provide some guidance in defining an operational definition of what it means to be Earth-like. So if we're truly interested in characterizing rocky bodies, we probably want to be focusing on the planets that are smaller than 1.6 Earth radii. Okay. So for the second point, which planets are rocky? Well, I haven't necessarily answered that question directly, but I can tell you which planets are not rocky. And by the time you get up to 1.6 Earth radii, most planets are not rocky at that size. Okay, and now let's move on to this third question. How Earth-like are these rocky exoplanets that we're characterizing? Well, to a large extent, this is an open question, and one of the motivating questions in the exoplanet field. So today I'll just give you a partial answer, but let me address this by first describing a case study. So I'd like to introduce you to the Kepler-36 planetary system, and this is one of my favorites, since I find it just truly amazing that the Kepler mission has measured the properties of a rocky planet 470 parsecs away with a precision comparable to that with which we knew the properties of the solar system bodies before the invention of radar ranging and interplanetary spacecraft at the turn of the 1900s. So this planet system consists of 2 planets discovered by Kepler transiting a subgiant star. And the extreme precision attained on the masses and radii of the planets, where the masses have been measured to better than 4.6% and the radii to 2.4% precision, respectively. That extreme precision of those measurements is due to the confluence of detectable solar-like oscillations in the host star, transit timing variations, perturbations in the time of arrival of the transits of the 2 planets, as well as dynamical stability considerations. So I've been collaborating with Jack Lissauer and Kat Deck to essentially revisit the Kepler dataset for this planet system to try to further refine the mass and radius measurements using the longer time baseline of Kepler data in hand since the initial discovery papers. Okay, so here's just a plot of the transits of the two planets in the Kepler data. And so you can see how the outer Kepler-36c has a far larger transit depth, is a much larger planet than the inner Kepler-36b. And though you may not be able to see it by eye, the transits in this time series don't recur like clockwork on a periodic interval. Rather, the system exhibits significant transit timing variations, which I'm showing here in this river diagram. So in this plot, each pixel is a representation of the Kepler photometry. Each row is a transit of Kepler-36b on the left and Kepler-36c on the right, where blue values represent lower values of the apparent brightness of the star, and green are higher values. Gray is where there's some data missing. And so we start with the first transit detected here at the bottom, up to the more recent transits towards the top. And so the blue river represents where Kepler-36c is in transit. And Eric Agel likes to call this a marsh diagram. It's a bit lower signal to noise. But you can still kind of see by eye the transits of Kepler-36b. And so this anti-correlated sinusoidal pattern gives a degenerate constraint on the mass and orbital eccentricities of the two planets. But of course, this chopping signal, which Eric Agel and Kat Deck have studied extensively, helps to break this degeneracy. So this, you can notice these large discontinuities in the transit times detected by the planets from one transit to the next. Here's one, there's another up here. And this is a result of close encounters. So this helps to break the mass eccentricity degeneracy in the solution to the transit timing variation time series, and helps to yield precise masses and radii, or precise masses for the two planets. Now, I just want to emphasize that the orbits of these two planets are extremely close. So their mean semi-major axes differ by less than 13 thousandths of an AU. So the planets are so closely interacting that, in fact, several of the solutions to the photodynamical fit, the Kepler time series, when Kat Deck integrates them for a series of giga days, many of them go unstable. So by winnowing down our solutions to this system, to only those that are long-lived, to within the duration of Kat's integrations, we can further refine the measured masses and radii of these planets. Ultimately, the mass of Kepler-36b is measured to within 4.2% relative uncertainty, whereas the radius is measured to 1.8%. And so here I'm showing samples from the posterior mass radius distributions for the two planets in red on this diagram. So here's Kepler-36c, the outer lower density planet out there, and Kepler-36b, the close-in rocky planet. And so Kepler-36c, it's such a low density that it requires several percent of its mass to reside in a hydrogen-dominated envelope. In contrast, you can already see by eye that Kepler-36b is very consistent with an Earth-like composition. But we can do a bit better than just looking by eye by coupling these mass radius posteriors derived from a photodynamical fit to the Kepler data, winnowed down by Kat Deck's dynamical stability analysis, to a model of the planet interior structure, we can actually try to constrain or get initial constraints on the bulk composition of Kepler-36b. So here's what we've done, and this is for a model where the planet consists of an iron core surrounded by a silicate mantle. And so for this two-layer model, there's a one-to-one mapping between a mass-radius pair and a core mass fraction. And so when we translate the mass-radius constraints of this planet directly into an inferred posterior distribution on the iron core mass fraction, this is what we find. So we essentially measure the iron mass fraction of Kepler-36b, conditioned on this particular model, to be 33 plus or minus 5%. So this is very consistent with an Earth-like composition. So the Earth's core consists of, or accounts for about 32.5% of the Earth's mass. And notably, a Mercury-like composition with 70% by mass in iron is ruled out. It's off this plot. Now, another thing just to note is that in this case, actually the mass, you'll note the mass and radius measurements of Kepler-36b are somewhat correlated. And this is largely due to the astroseismic constraints on the planet's host star. So the astroseismology actually constrains the host star density better than the perpendicular or orthogonal stellar mass radius direction. And as a result, the mass and radius derived for Kepler-36b is also correlated, where kind of a direction near the density is, with changing density, is better constrained than the orthogonal direction. And so this really actually helps us refine the composition constraints on Kepler-36b, since the long axis of this posterior distribution is nicely aligned with this Earth composition mass-radius diagram. It's less helpful in the case of hydrogen volume-dominated planets like Kepler-36c, because for planets with hydrogen envelopes, the mass-radius relationships are flat. I just mentioned this to illustrate how when deriving planet masses and radii, it's far better to sample from the entire posterior distribution in order to derive compositional inferences instead of just using the point estimates. Okay, so this was an example for essentially the rocky exoplanet, which to date, we have the best constraints on its mean density and bulk composition. But of course, there's a lot of effort being invested into characterizing the masses and radii of other rocky bodies. And as Dressing et al. Noted, among the whole sample of small planets characterized to date with mass and radius uncertainties smaller than 20%, essentially all of these planets with mass radius measurements are consistent with having an Earth-like composition. Now, there is one little underdog planet, one little chink in the armor that might be bucking this trend a little bit. So let me mention this little planet, KOI 1843.03. And perhaps I shouldn't actually call it a planet, because technically it's just a planet candidate. So you may want to take everything I say about this little guy with a small grain of salt, because it hasn't been statistically validated. But there's also no obvious reason to distrust this little planet either. So this is the current record holder planet that has the shortest orbital period among any detected to date. So it's 0.6 Earth radii, and it's whizzing around its star with an orbital period of 4.2 hours. So next weekend is Canadian Thanksgiving, and essentially you can cook a turkey in 1 year on this planet. Now, the fact that this planet, and I should say it's orbiting a star that's around half the mass, half the size of the sun. Now, the fact that this planet is still intact as a planet, so close to its host star, actually places interesting constraints on its composition. So you're familiar with the concept of the Roche limit, but you've perhaps know it best in the context of stars and falling into supermassive black holes, or maybe moons orbiting Jupiter and Saturn. But here we get to apply it in a new scenario in terms of an roughly Earth-sized rocky planet orbiting a star. So as a planet gets closer and closer to its star, it becomes tidally distorted, and at a certain point, the tidal forces overcome the planet's self-gravity, and it'll be tidally disrupted. And this closest orbital period, or orbital separation, is called, before tidal disruption, is called the Roche limit. And it's a neat little exercise to show that when expressed in terms of orbital period, instead of orbital separation, actually, the Roche limit doesn't depend at all on the properties, on the mass and radius of the host star. It depends only on the mean density of the orbiting body. So this is great, this is wonderful, since with Kepler we measure the orbital periods of these planets very well. But it can be challenging to characterize the properties of the host star. So the fact that KY 1843 has survived on an orbital period of 4.2 hours essentially implies that its mean density must be at least 7 grams per centimeter cubed. So we can again go back to our planet interior structure models to see what does that mean for the planet's composition. So I'm again using a 2-layer model here, but now plotting the minimum allowed orbital period in hours on the horizontal axis and planet size on the vertical axis. And each of these curves is for a constant planet composition, stepping in increments of 5% in mass from a pure silicate composition to a planet with a 5% by mass iron core, 10%, 15, all the way up to a pure iron sphere here on the far left. And now let's plot the properties of KOI 1843.03 on this diagram. So its orbital period is measured very precisely by Kepler data, but its radius is a bit more uncertain here. But you can already see that essentially KOI 1843.03 must be at least 70% by mass iron. So it must be at least as iron-rich as Mercury. So this little planet, whizzing around its star, is perhaps currently the first and only iron-enhanced exomercury candidate, exoplanetary candidate that we have to date. Now, what I said before wasn't 100% correct. I apologize. Because in fact, this Roche limit orbital period doesn't just depend on the mean density of the planet, but also on the distribution, the density distribution throughout the planet's interior. And so this initial composition constraint from Rappaport et al. Was derived by interpolating the Roche limits derived for single component polystropes. But of course, a single component polytrope is not necessarily an appropriate model for a rocky Earth-sized planet. So as part of her senior thesis, and some of the computers here at the CFA are churning away on her models now, Ellen Price has been modeling the 3D tidal distortion of rocky Earth-sized planets near their Roche limits. And so you should get her to give a talk sometime soon to give you updated, refined composition constraints on this fascinating little planet candidate, KOI 1843.03. But I think it's fair to say the fact that it's still substantially more iron enhanced than the Earth still stands. Okay. So in terms of this question of how Earth-like are rocky exoplanets, well, we've seen among the sample of planets for which we have mass and radius measurements, Kepler-36b and the rest of its cousins have compositions that are consistent with having an Earth-like iron to silicate ratio. So now I've kind of gone through all the three key questions that I set out to address. So we saw that small planets, at least on these close-in orbital periods, are common, that most planets larger than 1.6 Earth radii are not rocky, and that the majority of rocky exoplanets with well-measured masses and radii to date have bulk compositions that are consistent, or bulk densities that are consistent with Earth-like compositions. But of course, just constraining an iron to silicate ratio isn't really the only thing we'd like to know to really call something Earth-like. We'd love to know about the composition of the atmosphere. Does the planet have a magnetic field? What's its rotation rate? At this point, in terms of characterizing rocky exoplanets, we're really just scratching the surface. Actually, we're literally just determining if these planets have rocky surfaces or not. So, in this last portion of my talk, I'd like to take a journey to the future to try to see or extrapolate what we might learn about rocky planets, and particularly the rocky gaseous planet transition in the coming years. So there's a whole suite of space-based transit surveys on the horizon that will discover many more transiting planet candidates around bright nearby stars. And these transiting planet candidates will be far more amenable than the Kepler planet candidates were for ground-based radial velocity follow-up. So I think we can safely predict that the planet mass radius diagram will continue to be populated in the years to come. And so what might we hope to learn then as we accumulate more and more planet mass radius measurements? What insights can we glean from the underlying composition distribution of planets from this noisy sample of mass radius measurements? Well, to try to address this question and essentially do some exoplanet forecasting can complete a bit of a trade study. So here we come up with a parameterized model for the planet mass composition distribution and use this to generate a simulated sample of planets. We then add noise to derive a simulated sample of planet mass, radius, and orbital period measurements. We can then apply our hierarchical modeling techniques to try to infer constraints on the parameters of our planet mass composition model, and then see how well the output parameters that we infer agree with the parameters we input initially. So let me now just take some time to describe the parameterized mass composition distribution model that I'm employing for this work. So here, since I'm still interested in understanding the transition between rocky and volatile rich planet populations, I'm taking a two-component mixture model, considering rocky planets consisting of an Earth-like rocky composition. And perhaps this is a model population that finished its formation after the protoplanetary gas disk dissipated. So it never managed to accrete or retain a hydrogen-helium envelope. Whereas the second component of this mixture model corresponds to planets with hydrogen-helium dominated gas envelopes. So these are perhaps planets that formed more quickly before the gas disk dissipated and did in fact manage to accrete a hydrogen-helium dominated envelope. And then to parameterize the mass composition distribution, you do so in this way. So for the rocky planets, and for simplification, I'm taking the iron to silicate mass ratios fixed, but I'll parameterize the mass distribution of rocky bodies as a log normal distribution. So this has two parameters, essentially the mean mass and the amount of dispersion. I'll use a similar distribution to parameterize the core masses of the gaseous planet population, and then take a power law relationship between the mean, a power law mean relationship between the envelope mass expected for a given core mass. But we expect there to be some dispersion about any mean relationship in the outcomes from planet formation. So this physical dispersion in the envelope mass expected for a given core mass is an additional parameter. And finally, the last parameter is the fraction of planets in this rocky planet category. So here we have what I would call perhaps the most distilled planet mass composition distribution parameterization that we might hope to achieve, that still encapsulates a lot of the physics that we'd love to constrain. So this has 1, 2, 3, 4, 5, 6, 7, 8 parameters. Okay, so taking noise, adding noise to the planet mass radius measurements that is characteristic of the mass and radius uncertainties achieved in the Marcy et al. Catalog of Kepler planets with Keck radial velocity follow-up, we can explore how well do we do at recovering the input parameters. So here are the input parameters that I chose. The specific values don't really matter. I'm showing this mass radius diagram now, where the black points are the true exoplanet discoveries, and the red points are just one iteration of a simulated planet sample, just to convince you that I'm not taking totally outrageous input parameters to make it super easy for me to recover the input values. So just by eye, the distribution of my simulated planet mass radius measurements is not too different and rather similar to the current sample of exoplanet mass radius measurements. And you can see many of these are just simulated mass upper limits, in fact. So now, if we consider 50 planets and do a recovery multiple times to explore if there are any biases, we can see how well we do at recovering the input parameters for each of the 8 parameters. So each panel here represents one of the parameters, and the red line is the value input, whereas the blue lines are the median, and the blue points give the median values, and then the blue lines range from the 25th to 75th percentiles. And so with 50 planets and around a meter per second lower limit on the radial velocity uncertainty, we recover the input parameters with uncertainty of perhaps on order 40%. Looking to an optimistic future with tons of telescope time devoted to exoplanet radial velocity surveys, with 260 planets, we can recover the input parameters to around 10% relative uncertainty. Now, love to get an idea from Dave how realistic or plausible this might be, but perhaps it's not too outlandish for the Kepler transit timing variation sample, studying planets near mean motion resonances. And this, of course, real life will be a bit more complicated than this, because here I'm analyzing a sample of simulated planet populations where the model I'm using to generate the simulated planet population is the exact same one I'm using to try to extract the constraints. But nonetheless, I think this is rather encouraging that even with mass radius uncertainties typical of those being achieved today, just by adding larger numbers of planets, we can hope to gain a lot. Really leveraging the opportunity that exoplanets provides us to study large numbers of planets to refine our insights into the compositions, distribution of planets overall. And so these are some of the questions that I think are ripe for empirical constraints as we accumulate larger and larger numbers of planet mass radius measurements. What's the typical mass scale of rocky planets? What's the relationship between core mass and envelope mass? Is there evidence for distinct planet subpopulations formed through distinct planet formation pathways? And then how much physical scatter is there in exoplanet compositions? So I think there's a lot to learn. There's a lot of exciting discoveries on the horizon. And I look forward with anticipation as we continue to place empirical constraints on the settings of our science fiction stories. So, thank you.
Thank you very much. We'll take questions from the audience. That's not working? Oh.
Here, take questions from the audience.
For your very small Mercury planet, is the expectation that the atmosphere has been photoevaporated for that, since it is obviously so close to its star?
Yes. Oh, okay. So the question was, for the very small exomercury planet, KOI 1843.03, is the expectation that it doesn't have an atmosphere because the atmosphere would have been photoevaporated. And so, yes, that is indeed the expectation, but I would also note that even if it did have some sort of volatile layer that would be contributing, that would only further increase the need for an even higher iron mass fraction to compensate. So indeed, it's likely that the envelope has been photoevaporated, both based on photoevaporation models, but also based on the high apparent mean density of the planet as well.
Jason?
So another question about that black card. You were assuming that only the self-gravity is important. Is like the energy to separate the iron, like the crystalline structure, relevant here, or?
So that's an excellent question. It is. Oh, sorry. Thank you. So the question was, is essentially the material strength of the rocky planet near its Roche limit relevant in this calculation? And the answer is no, in this case, for rocky bodies that are larger than a few hundred kilometers in radius, the self-gravity dominates the material forces. So that's kind of why we don't have square planets, and the planets have relaxed to a hydrostatic equilibrium shape. Those material forces are relevant for people considering tidal disruption of asteroids. So there is, yeah, your intuition is right. There is a regime in which the material forces are important to consider. It's just not relevant for KOI 1843.03.
So you started us out with Earth and Neptune,
Yes.
which you also called an ice giant.
Yes.
You did talk a lot about water in your models. I'm just
Yeah.
wondering what role water plays in this story.
That is an excellent question. And one, well, we would love to constrain the water abundances of these low mass, low density planets that have been discovered by Kepler. The thing is that's challenging just due to the degeneracies in interpreting a mass radius measurement. Since water is intermediate in density between the rocky and material and hydrogen helium, essentially the ice to rock mass ratio is completely unconstrained from a mass and radius measurement alone. Although we would love to know the water mass fraction of these planets to try to say something about, did they form in situ where we see them today, close to their stars, or did they form beyond the snow line and then migrate inwards? So actually, the title of my second fellowship at Berkeley is Searching for Water in Distant Worlds, and so I'm actively trying to explore theoretical pathways towards constraining the water abundance on these planets. But it's a challenge, even getting atmospheric transmission spectroscopy, whether the planet is just a rock hydrogen-helium mixture, or if there's a significant mass fraction of water in its deep interior, you'd expect to see some water in the spectrum no matter what. So the composition of the very outer layer, you require the planet interior structure models to really extrapolate it into the composition of the bulk planet. So empirically, we don't know. It's plausible. There are some theories that these planets that we're seeing in Kepler with these low masses, low densities, did form in situ and managed to create a hydrogen-helium envelope. So it is a plausible scenario that they only have trace amounts of water anyway, but empirically we don't really know yet. So it's an exciting research question.
Would albedo help to break that degeneracy in Charles's question? I mean, if you could do it in a future telescope.
Would albedo help to constrain the water abundance in the planet?
In other words, if you have a range over which you just don't know where the ratio is between rock and gas, in which you can play with these parameters of certain fractions of rock, water, and gas, whether albedo can help break that.
Yeah, so I would say it might. So I've chatted a bit with Brice-Olivier Demery with this, because he's, in the Kepler data set, he's done the most comprehensive job constraining the albedos of planets from the Kepler data set. And my answer would be, it may provide some help in constraining, or at least giving kind of an independent source of confidence for the planets to distinguish whether they have a rocky surface or some sort of a volatile envelope. We might expect a rocky surface to have a lower albedo than an atmosphere, but I think it would still be difficult to use albedo to constrain the bulk water abundance of these planets. So we don't even know, even though we call Uranus and Neptune ice giants, you can come up with completely plausible interior structure models that just use rocky material and hydrogen helium that fit all the observed data. So it's difficult to extrapolate from the atmosphere to the interior, except in some special scenarios.
So I just want to understand the parameter recovery simulations that you're showing at the end of your
Yeah.
a little more. Because they really bear upon the goals of tests.
Right.
And we just had our big test science team meeting yesterday.
Yes.
So you said you assumed uncertainties in the masses and radii typical of the current situation. The trouble is right now, there's really no typical error bar.
Right.
Some radii are very well determined for the subset of stars that have astroseismology. And on the
Yeah.
radial velocity side, for example, from the Marcidal paper, the majority of systems were only upper limits. There wasn't even a measurement.
Right.
So could you just tell me exactly what did you assume a fixed precision in radius and in mass, or?
No. Oh, okay. Yes.
Well, that was
So,
long.
yeah. So Dave was asking for more insights into exactly what I assumed for the uncertainties in the masses and radii of the planets in my simulations. So let's see if this comes up. So here I'm just showing the distribution, the relative, these are histograms of the relative radius uncertainty. So sigma, 1 sigma divided by the measured planet radius for in the Marcy et al. Catalog, as well as the relative uncertainties on the radial velocity amplitude.
And that, so many of those are greater than 1.
Yes, yeah. So
They're not.
So this isn't, the uncertainties on K are in meter per second, right? So I took, essentially, I fit truncated Gaussians to this. So to try to at least give a first pass description of this distribution. So none of the uncertainties on the planet radius in my sample are better than 2%. And none of the, I actually truncated this a little bit more conservatively so that none of my simulated planets had measured K values better than 1 meter per second.
That's great. My
Although the orbital period distribution I took might not be representative, and that folds into this, but.
Just because you've asked if we could do 260, we can do 260. But my feeling is for tests, because, for example, you'll have parallaxes where you don't have
Right.
that cover. And because the stars will typically be 100 to 1,000 times brighter, the RVs will be so much easier. I think that you won't have to do 260, but you'll do 50 to 100 really well, much better we could have ever done.
Okay.
Using the Marcy uncertainties is the most conservative case.
Yeah, so
Yeah.
this is very conservative, but I think there's reason for well-founded
Okay.
optimism.
Yeah, so part of what I can do with this framework is actually explore, given some mapping between like how much telescope time each of these mass radius measurements represents, explore for a finite amount of ground-based telescope resources, what is the optimal number of planets to pursue? If you're interested in making these population level constraints, is it better to get fewer with even higher precision masses, or to cover a larger number with less precise masses?
We have time for one more question. Okay.
A minute ago, you mentioned the role of transmission spectroscopy in probing the atmospheres of transiting exoplanets. Does what you can learn about the atmosphere that way give any sort of handle for helping to constrain the composition?
So, yes, it certainly does. An excellent example is GJ1214b, where that planet has a mass and radius such that sufficiently low density that it requires some sort of a volatile envelope, but not so low density that it's unambiguously a hydrogen-helium envelope. Oh, if the planet were more than 50% water, that would fit its measured mass and radius. So there, by getting atmospheric transmission spectra and trying to constrain the mean molecular weight of the atmosphere by measuring the atmospheric scale height, you can try to distinguish between a hydrogen-rich versus water world scenario. In practice, for that particular planet, high-level clouds or hazes are blocking our view of the absorption features. So it didn't work out for that one, but there has been a reported detection of a water absorption feature in HAB P11b, and so that gives us some hope that there's some subset of these Neptune-sized small planets with transparent atmospheres so that we can use atmospheric transmission spectroscopy to gain some insights into the planet bulk composition.
All right. Well, let's thank Leslie once more.